In this PowerPoint lecture, we're going to cover the complex math that we need for our forced or steady-state sinusoidal excitation analysis that we're now covering in ENP 231. So let's get started. In our number system, we think of positive numbers as corresponding to the distances measured along a line starting from an origin. So for example, plus 3 is a line pointing from 0 to the right to 3. Negative numbers enable us to solve equations like x plus 2 equals 0, and they can be represented by distances to the left of the origin, such as minus 4. Numbers corresponding to distances along the above line are called real numbers. To solve equations like x squared plus 4, so-called imaginary numbers were defined or invented. Imaginary numbers are plotted along the imaginary axis, which is chosen to be orthogonal with the real axis. We use J in the circuits or electrical engineering just so it doesn't get confused with I. So that could be J1, J2, or 1J, 2J. We're going to use J1. We'll put J at the beginning, and that reason will become apparent here shortly. This adds a second dimension to our numbering system. And note that all numbers are abstractions, whether they're real or imaginary. Think of the J operator, J as an operator, kind of like square root or sine or the minus sign. So the minus sign operating on a directed line segment reverses its direction or rotates it by 180 degrees. The imaginary operator J can be thought of as a 90-degree counterclockwise rotation operator. So here we operate on plus 3 with J, and it rotates it 90 degrees. And then we operate on it again with J, and it rotates an additional 90 degrees. So operating on plus 3 with J and then J again, or taking that operation twice, yields a minus 1, or is equivalent to a minus 1 operation, or 180 degree rotation. Some properties of JB. When we see something like J operating on JB, we think of that as J squared operating on B. And J times J, think of each time as a rotation of 90 degrees. J squared is essentially a rotation, counterclockwise rotation of 180 degrees, and we can replace that with minus 1. This leads us to being able to write J squared is equal to minus 1, or J cubed is equal to minus J, or J to the fourth as plus 1. But these statements, J squared equal minus 1, is really a statement that two operators are equivalent, and does not imply that J is a number, although we do think of it that way, and that's probably how you learned it when you studied complex math in high school. Conveniently, in all the algebraic operations that we'll be doing, imaginary numbers can be handled as if J had a numerical value of square root of minus 1. But the proper way that we'll be thinking of J is, again, as an operator that rotates whatever number we're operating on by by 90 degrees in the counterclockwise direction on our complex number plane. So the real and imaginary axes define what we call the complex plane. A complex number on this plane may be interpreted as a point or a vector on the plane. We designate a complex number W as having a real part A and an imaginary part W. So we would write W is equal to A plus JB. RE, or the real part of W, is A, and IM, or the imaginary part of W, is B. Note that the imaginary part of W is not JB. So in other words, the real and the imaginary parts of a complex number are both always real. two complex numbers are equal if and only if their respective real parts and imaginary parts are equal. W can be represented in rectangular or polar form. So W is equal to A plus JB, and we've plotted that here on the complex plane. Real axis is horizontal, imaginary is vertical, and we have a base that is a length A and a rise, or a vertical side that is of length B, and we can define an angle theta, which is the arctangent of B over A, and a hypotenuse that is the square root of A squared plus B squared. So we can actually describe this complex number in either Cartesian coordinates, rectangular, as A plus A comma B, if you will, or A plus JB, or as in polar form, where it would be magnitude C angle theta, and that's what that C kind of greater than equal sign looks like, is meaning. The greater than equal sign is really just angle, so it's magnitude C angle theta, where we have defined C and theta accordingly. Be careful though, because inverse tangent is multi-valued. It's defined from pi plus pi over 2 to minus pi over 2. So the arctan of minus 1 over plus 1 is minus 45. But the arctan of plus 1 divided by minus 1, that puts you, the rise is plus 1, the real value is minus 1, so that puts you over in the third quadrant, the top left quadrant. That has a value of 135 degrees. But if you just take the arctan, in both those cases you're taking the arctan of minus 1. So on your calculator you take the arctan of minus 1, you're going to get minus 45. But you need to pay attention whether the numerator or the denominator had the minus sign. All right, arithmetic operations. So we're talking about addition, subtraction, multiplication, division. When you're adding, it is best to add using rectangular coordinates. The real parts add, the imaginary parts add. Same with subtraction, do it in rectangular form. When you do multiplication, you certainly can do it in rectangular form, as is shown right here, but it'll turn out that actually multiplication is better done in polar form. So I don't know if I have a slide on it, but when you do multiplication in polar form, you simply take the product of each of the magnitudes and then you add the individual angles, which is a lot easier than doing all the cross products as you see here, which is what you would do if you were in rectangular, using rectangular coordinates. For division, we have to do a little trick. So let's define complex conjugate of W. We use W star or asterisk. And so if W is A plus JB, then the complex conjugate is A minus JB. So it has the opposite sign for the imaginary part. Then it turns out always that the complex number times its complex conjugate is equal to a real number, and the cross products, cross terms cancel, and you end up with A squared plus B squared, which is always a real number. Notice that that is actually the square of the hypotenuse if you were to draw, if A and B were two right angle sides of a triangle, as we saw in the previous slide. So the way that we do division is if we divide W1 by W2, we actually do W1 times W2, the complex conjugate of W2, divided by W2 times the complex conjugate of W2. And here basically it converts a division into a multiplication. So we end up multiplying W1 and the complex conjugate of W2. And then we divide the whole thing by basically the magnitude squared of W2, which is, W2 times the complex conjugate of W2. Similarly to multiplication, an easier way to do division certainly if you already have W1 and W2 in polar form, is you simply divide the magnitudes and you subtract the angles. Okay, what about our complex exponent? So we're studying this because we're in the middle of looking at these e to the st excitations. And if we have s to be a complex value, minus alpha plus j omega, so alpha would be a real number. Let's assume it's positive, so that minus alpha is a negative real value, and omega is a real value. Then we have this e to the minus alpha t, which is an exponential decay, times e to the j omega t. And what is e to the j omega t? Can we relate this to our complex plane? And the answer is yes, we can do that by Euler's identity or Euler's formula. So you've seen this before, where Euler showed that e to the j phi is equal to cosine phi plus j times sine phi. And here's a diagram on the right. It's on the complex plane, so real values on the real axis, on the horizontal axis, imaginary values on the vertical axis. And if we draw a line, a vector, and it has a base, a real component of cosine phi and an imaginary component of sine phi, okay, and it's on a unit circle, so it has a magnitude of 1. We can then write this cosine phi plus j phi, which is a rectangular form. We can write it equivalently in its polar form, where its polar form has a magnitude, in this case 1, and an angle, which in this case is phi. So to prove Euler's identity, let's look at the Taylor series. So here we have the Taylor series about a point A, and we're going to be looking at it about a point A equals 0. We're going to do this for sine x. And if you do the math, it turns out that sine x can be expanded as x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, etc. All right, and what you see here is those first 4 terms actually will trace out that, what is that, purple or magenta line, and you get pretty good approximation for a half a cycle, a half sine wave on either side of 0. And then here to the right we see another plot where we're using many more terms, and you can see as you increase the terms, the fit will follow a sine wave further and further away from x equals 0. Now for e to the x, we can do a Taylor series, and that evaluates to 1 plus x over 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc. Now this is how we can show that or prove Euler's identity. So we'll use Taylor series about a equals 0, which is actually called the Maclaurin series. We can write cosine, sine, and e to the z as power series. All right, so we saw before that, for instance, sine of theta is theta minus theta cubed over 3 factorial plus theta 5th over 5 factorial, etc. Turns out the cosine of theta can be expanded as 1 minus theta squared over 2 factorial plus, and you see the power, so it's going to be even powers of theta. Now if we add those two together, cosine theta plus, and not, instead of saying plus sine theta, if we say cosine theta plus j sine theta, and we use those two power series, we end up getting a power series that has all powers of theta, both even and odd. And all of the odd powers of theta have a j in front of them. Then what we do is we write the power series for e to the z, and that turns out to be 1 plus z squared over 2 factorial plus z cubed over 3 factorial, etc. And then finally we basically do a substitution, replace z with j theta. And when you plug that in, whenever you have an odd power of z, so z cubed, you end up with theta cubed and then a minus j in front of it. That's our final step. And now we can conclude by looking at the e to the j theta expansion and comparing that to the cosine theta plus j sine theta expansion, we see that these are in fact the same power series. So therefore, e to the j theta is equal to cosine theta plus j sine theta. Now there's a second proof, which I won't go through here, but it's you can take a look at this slide. You can also look it up on, I think, on Wikipedia. And this is another proof for Euler's formula. So in summary, if we're given a complex number w, we can represent it in either rectangular or polar form as a plus jb, or ultimately as c e to the j theta, or written in shorthand as c angle theta. And the connection between the two is that the real part A is c cosine theta, and the imaginary part B is c sine theta, where c is related to a and b according to the square root of a squared plus b squared, and where theta is related to b and a as the arctan of b over a. When we do arithmetic of complex numbers, it's handy to follow the following guides. For multiplication, it's best to do this in polar form if possible. We multiply the magnitudes and we add the phases. For division, we also do that in polar form by dividing the magnitudes and subtracting the phases. For addition and subtraction, it's best to use rectangular coordinates, where we simply add the real components or subtract them and add or subtract the imaginary components.